Alright guys, new unit here, and this is going to be a really fun one too. Chemistry is pretty sweet. You guys haven't had the opportunity to really look at what chemistry is all about yet. This is going to be your first year looking at the big old bad periodic table of elements. What chemistry is, let's start right there. Chemistry is a branch of science that is exploring all of the different matter that exists. So matter is all the things you can touch. It's all the things you can see. There's two main classifications of stuff in the universe. There's energy and there's matter. So again, matter is all of the stuff that you can touch. What chemistry looks at is matter. It explores how matter moves. It explores how matter combines together. It explores the basic structure of matter, like what those molecules are. That's what the periodic table of elements is all about. Those are the basic building blocks of all of the matter in our universe. One of our main goals as scientists is to understand our universe around us. So it helps to be organized. Just like your notebooks, you would have a tough time reading through your notes. I'm sure some of you do, if they're all over the place. So we like to organize things. We like to put them in nice, neat, logical groups. So we do the exact same thing with matter. We've clumped it together, we've grouped it, we've organized it. So we're going to be exploring that a little bit today. But without any further ado, we got to get some mixtures on the.
Alright, how's this for revenge? A solution of hydrogen peroxide and one of saturated potassium iodide.
What's this?
Mountain Dew. Ah, refreshing. Now, we're going to combine these chemicals with ordinary dish soap, creating a little exothermic release of oxygen.
Foamy vengeance.
Yes, exactly.
This is brilliant, Sheldon. How are we going to deploy it in Kripke's office?
Already taken care of. Observe. This is a live shot of Kripke's lab via a mini webcam I was able to install thanks to a dollar bill discreetly placed in the night janitor's shirt pocket. At the same time, I also secured large quantities of these chemicals above the tiles in the drop ceiling.
Sheldon, you remind me of a young Lex Luthor.
You flatter me, sir.
Let me guess, motion sensors?
Yes, the reaction will be triggered when Kripke reaches the center of the room. Mwahaha.
I gotta say, I am really impressed. This is truly the Sheldon Cooper way to get even.
It may be low tech, but I still maintain the whoopee cushion has comic validity. Here comes Kripke.
Who's that with him?
I believe that's the president of the university.
And the board of directors. Abort! Abort!
There is no abort.
Well, how could you not put in an abort?
I made a boo-boo, all right?
I think the board will really appreciate how well we're using that NSA grant, President Seba. Right here we have a micro-controlled plasma.
Wow, looks like the Ganges on laundry day.
At least they don't know it was you.
Hello, Kripke. This classic prank comes to you from the malevolent mind of Sheldon Cooper. If you'd like to see the look on your stupid face, this video is being instantly uploaded to YouTube. Oh, and a hat tip to Leonard Hofstadter and Raj Kuthrapali for their support and encouragement in this enterprise.
Well, I'm going back to India. What's your plan?
So, how did Sheldon do that? How did he come up with this master plan to get back at Kripke? He used a chemical called hydrogen peroxide, which is the starting chemical inside of the graduated cylinder here. Also in there is just dish soap. When the other chemical is added, called potassium iodide, this explosion of foam happens. So let's go over how that happens. First of all, hydrogen peroxide naturally undergoes a chemical reaction with itself called a decomposition. It breaks itself down. H2O2 is hydrogen peroxide, and it breaks itself down from H2O2 to water and oxygen. Oxygen's a gas. When the potassium iodide is added to the hydrogen peroxide, it starts decomposing really quickly, and it starts releasing this massive amount of oxygen. The dish soap serves to capture the oxygen. All of this foam is really just bubbles of dish soap that is capturing pure oxygen. And the oxygen, again, is coming from the breakdown, the chemical change, the breakdown of that hydrogen peroxide into two different things. Now, the oxygen that's coming out, it's no longer hydrogen peroxide. The water that's coming out is no longer hydrogen peroxide. That is chemistry. We're looking at how matter can change. Matter can chemically react with other things, and you end up with a brand new result. As fun as chemical mixtures are, move on from there.
For now, we'll be back to mixtures and reactions later in the unit. So let's tackle the idea of organizing matter. There's several different reasons to organize matter, and good reasons to organize them in different ways. WHMIS is one way that we categorize chemicals based on their dangers, and it's a great system because it's a global system. Virtually everybody on the planet has agreed on the same chemical naming system, again called WHMIS. WHMIS stands for Workplace Hazardous Materials Information System. That is it's an important system, because imagine making something in Japan, and then like a chemical, and that's poisonous, and then they ship it over to Germany, and then the Germans take it and manufacture it, and then sell that chemical in smaller doses inside of something else, say Raid, over to somebody in the U.S. or somebody in Canada, and so that chemical has changed hands several times. Using a common naming system between all three of those countries, between all languages, really, you can ensure people stay safe from chemicals. So we're going to explore WHMIS in a little greater detail. So we're going to do a basic breakdown of WHMIS. It does get a little bit more complicated than this, but at the basic level, for the majority of people that are concerned with WHMIS, it's pretty much everywhere. You can't even work at McDonald's without understanding WHMIS, because you're using chemicals there, industrial chemicals, and you need to understand what's in there, what the dangers are. So WHMIS, you're not going to escape it. Anybody. So let's go over the basic ones, because that's the basic understanding that most people need. So first of all, there's Class A. Class A is compressed gases. The symbol looks like a typical gas cylinder that's used to house acetylene or oxygen or carbon dioxide or any gas. Compressed gases have some pretty interesting dangers. The big one being, if you were to increase the temperature of the compressed gas, you are drastically increasing your chances of that compressed gas trying to get out. If there is a leak that springs in the top of the valve, if the valve can't hold back the pressure anymore because you're increasing the temperature, the compressed gas canister can explode, or at the very least it can go flying across the room. Pretty dangerous. The next class is Class B. Those are flammable materials. So anything that can be lit on fire. Gasoline is an example of something that is flammable. Class C is an oxidizing material. So oxidizing, this one it looks like it's flammable, but it's not actually flammable. When it says oxidizing, it provides oxygen. The chemical, certain chemical reactions with that chemical will cause it to release oxygen into the environment.
why that's bad and why that's dangerous is because oxygen is one of the 3 main ingredients to fire. For a fire to burn, it needs 3 things. It needs heat, it needs fuel, and it needs oxygen. If you don't have one of those 3 things, you don't have a fire, period. So that's how firefighters actually fight fires. They tackle one of those 3 things. The purpose of the water is to take away the heat. They can do other things, like if you put a blanket over top of somebody, you're not necessarily removing the heat, but you're removing the oxygen. If you starve the fire, it goes out. So oxygen being a really important key aspect to fire, an oxidizing material doesn't produce its own fire, but it can contribute very dangerously to nearby fires, to explosive levels as well. Class D is materials that cause immediate and serious toxic effects. So they're ones where, like, if you consume this material, you're going to get sick, and you're going to get sick right now. And it could be dangerous. It could be something really serious and could be fatal. So these are materials that get absorbed into your body. They can get absorbed in several different ways. The one that's most commonly overlooked is absorption through skin. Your skin absorbs chemicals, including water, including stuff out of the air. Like your skin is constantly absorbing things. The other entryways into your body is through your eyes, through your air, so when you're breathing through your mouth or nose, and then finally through swallowing. So lots of different entry points. Any of them work. Sometimes really you can get poisoned just through absorbing through your skin. That's a very real concern with certain chemicals. Another Class D WHMIS symbol is this little T. It looks like a T. These are materials causing other serious toxic effects. These ones are different from poisons in that they cause an effect over a long period of time. So if you're constantly exposed to these toxins, they will make you sick over a long period of time. For example, carcinogens. Anything that causes cancer, it's not something that is going to make you sick right now, like the poisonous materials. It's something that will make you sick in the long run. Eventually, it will make you sick if you continue to expose yourself to it. There's many chemicals inside of tobacco that are carcinogens. That's why somebody that takes one cigarette, they're exposing themselves to something toxic, but it's the consistent exposure to that toxin that eventually can make you sick and develop cancer and other terrible things. The third Class D chemical is biohazardous infectious materials. Basically, this is anything that comes from a living organism. So if you have blood taken from you at a hospital, a biohazardous infectious materials stamp is placed on it. Not saying that you're infectious, but you could be. You could be housing bacteria inside of your blood that could be the next pandemic. And spreading that around is a terrible idea. So they're cautious with that kind of thing. They need to be careful. Basically, a biohazardous material is anything that could infect somebody else or something else with a pathogen, a disease-causing bacteria or virus. Moving on from Class D is Class E. These are corrosive materials. These are ones that will, like acids or bases, they'll actually start chewing through things. They react so chemically quick with certain things that they will chew through them. Like they'll actually burn right through them. And this is a different kind of burn, not a fire kind of burn, but a chemical reaction kind of burn, where like it'll actually start chemically reacting, for example, with your skin and destroying those cells with a chemical reaction. That's different from a fire, but nonetheless very, very dangerous. So corrosive materials, something to look out for. And finally, Class F. These are dangerously reactive materials. These are materials that will react violently under certain conditions. They will react really quickly and it will be out of control. So that's dangerously reactive materials. Those are the 6 classes of WHMIS symbols. So there's class A, B, C, D, E, and F. Keep in mind that class D is all of the poisonous things. So class D is 3 of them. The materials that cause immediate effects, materials that cause long-term effects, and then the biohazardous materials. All 3 of those things are class D. So there's 6 classes in total: A, B, C, D, E, F. Compressed gases, flammable and combustible materials, oxidizing materials. There's immediate and serious effects, toxic effects, biohazardous materials, and then finally the last 2 classes are corrosive materials and dangerously reactive materials. Another way, matter can be broken down into 2 different classifications. So pure substances, so it's just one thing, and then mixtures, so combinations of things. So let's first look at the pure substances. Pure substances are can also be further broken down. Pure substances could be broken down into pure elements and then compounds. So in an element, you're just looking at just one element. So for example, if somebody had a 24-karat gold necklace, that would be a pure element. The only thing in there is gold. Elements can form together to make something new. For example, sodium and chlorine. Sodium is a metal. It's a really soft metal. It reacts really violently with water. Chlorine is the stuff you put in a pool. It's poisonous. We put it in there to kill algae, bacteria. But it's at room temperature, it's normally a gas, a green gas. If you were to combine the 2 of them together, sodium and chlorine, you get salt. Yep, salt. Sodium chloride is the chemical name for salt. It's a combination of that soft metal and that green poisonous gas. That gives us salt. And that doesn't mean that salt is poisonous. It doesn't mean that salt is a soft metal. It's a chemical compound. So if you were to have a jar just full of salt and there's nothing else in there, that would be a pure substance. But it's not a pure element, it's a pure compound. It's just made of sodium chloride. So compound. Same thing with like a glass of water. Water is H2O. There's 2 hydrogens and 1 oxygen per molecule. And if you were to have a glass of pure water, that would be a pure substance, and it's a compound. Next is mixtures. So aside from pure substances, we can mix things together. There's 2 classifications of mixtures. There's heterogeneous mixtures and homogeneous mixtures. So let's start with heterogeneous mixtures. First of all, there's mechanical mixtures. So a mechanical mixture is when you have huge, very different particles. A salad, a pizza, those are great examples of mechanical mixtures. You can very clearly see the different bits that are inside of that material. Next are suspensions. Suspensions is when the particle bits are starting to get pretty small. For example, inside of murky water. It's murky because there's little bits of sand that are floating in it. They are suspended in the water. That suspension is again defined by the size of the particle. If the particle is small enough that it can stay afloat inside of the material but will eventually settle out, that's called a suspension. Orange juice is a good example of a suspension. The pulp in orange juice, it will stay floating inside the juice, but eventually if you leave it long enough, that pulp will settle down to the bottom of the juice. And I'm not saying leave it for like an hour, I'm saying leave it for a couple days. Suspensions, again, they're defined by the ability of particles to float inside of the liquid. Continuing with heterogeneous mixtures is colloid. Now, again, we're talking about smaller and smaller particles here. A colloid is where the particles are so small that they stay suspended indefinitely. Mayonnaise, for example, is a great example of a colloid. Fat particles inside of, or fat molecules, I should say, inside of the mayonnaise, they stay suspended in the mayonnaise indefinitely. They don't separate out. That's why it's called a colloid. Jello is another example. There's sugar molecules in there. There's lots of other things. Those molecules don't settle down. They stay exactly where they are. They stay suspended. Moving on from heterogeneous mixtures, there's also homogeneous mixtures. This is when the particles are so small that they've been broken down perfectly. They mix 100% with the solution. So, for example, mixing salt in with water or mixing sugar in with water, you get a complete dissolving. If the material, what dissolving is literally breaking the particle apart molecule by molecule. So when you have salt water, there's no chunks of salt in there. The salt has been, the cube of salt has been ripped apart by the solution. It's been dissolved so that it is evenly mixed inside. That is called a solution. When you have even mixing between the chemical that's the base chemical, in the case of salt water, that would be the water, and the thing that's being mixed in, again, in the case of salt water, that would be the salt. The difference between a heterogeneous mixture and a homogeneous mixture is really the size of the particle. As you go down the list, mechanical mixtures are very large particles, very easy to see. Suspensions are smaller particles that stay in suspension and can eventually settle out. A colloid is one where those particles are getting small, so small that they can stay suspended indefinitely. And then eventually a homogeneous mixture, solutions, is when you have complete dissolving, so 100% mixing. Chemistry is all about matter. It is a way of organizing things. So what we went over today was a way of organizing materials based on their dangers that they pose, and we also talked about organizing matter based on their physical properties, so kind of how they're mixed with each other or whether they're mixed at all, pure substances or mixtures. That's all for this one. Thanks for watching. Until next time.